Let us do an energy and entropy analysis of an open steady device, a turbine in this case. I've picked up a problem from chapter 4, and since this is a problem about the PG model, we'll replace steam with, let's say, air. At the end, we can come back and see what answer we get if steam is treated as a perfect gas. So let's see what is given in this problem. Air enters the turbine. The inlet conditions are given. We'll call it, say, state 1. And mass flow rate is given. An exit pressure is given. So at state 2, which will be our ideal exit state, and state 3 will be an actual exit state. So the pressure, of course, will be 200 kPa, whether the turbine is ideal or an actual turbine. Okay, so let's begin. First thing first, we draw a TS diagram showing the ideal and the actual turbine. Recall that the constant pressure lines looks like this. So this is the pressure line of 4 MPa for a perfect gas. Let's say this is state 1. So this is the 4000 kPa line, and the air expands to 200 kPa. So this will be a 200 kPa line, and in an isentropic case it will come down vertically, and we know that in an actual turbine the exit entropy will be slightly higher. Okay, so state 1, let's write down everything that is known. Pressure, I'm converting that to kilopascals. Temperature, instead of Celsius, let's go straight to Kelvin. And mass flow rate is supplied. Okay, to find state 2, we recognize that entropy remains constant. And what formula should we use for an isentropic case? So state 2, let's write down again. We know pressure. And we know the entropy at 2 is entropy at 1. So for PG model, the formula we open test, and if you go to the property tables, I'm showing that table one more time. If you go to table J, if you go down to table J, it's the formula sheet. I'm assuming you already have a printout of that. Go all the way to the bottom of this and you will find all the different material model, the equations, all the models separated. So this is our PG model. And in the PG model, you can see equation 11 is the isentropic. If entropy remains constant, use one of this convenient relationship. So look, if you know the temperature ratio, pressure ratio can be found, and vice versa. So we pick up this formula and go back. We recognize you can write, again, just to remind you, we have state 1 here, state 2 here. So the higher temperature T1 over T2 will be P1 over P2 to the K minus 1 over K. So that gives us T2 equals, we want to find T2 equals T1, which is 873 divided by what is P1? If you recall, this is 4000 and this is 200. So their ratio is what? 20 to the, and K value is well known. So it's 873 divided by 20 to the 0.4 over 1.4. Found state 1 temperature, state 1 is given, state 2 we've just calculated. So therefore, we can do a energy analysis for the turbine. The EDT m dot J1 minus m dot j2 plus q dot, right? So steady state 0 equal, and we are just writing j equals h, and w dot turbine is our ideal turbine. So let me write down ideal here to remind us that this is isentropic turbine. So therefore w dot t ideal, and if we use the formula for h1 minus ht, and T1 was 873 and T2 was 370. Is that what he calculated? Yes, 371. Once we calculate this, it turns out to be 2521 kilowatts. So that's the maximum power out of the turbine. Let's go and verify this. We already calculated the two states. Go to the device panel. We load state 1 and we load state 2 as inlet and exit state. Heat transfer equals 0. And it is 2521, exactly what we calculated. So we found the turbine power when the turbine is isentropic, that is its ideal turbine. Well, let's do the second part of the problem, that if the exit temperature, what was the second part? If the exit temperature is 220 degrees Celsius, determine the isentropic efficiency. So as you can see, if the exit temperature is 220 Celsius, which is state 3. So for state 3, now we know the exit temperature. Let's say 273. So therefore, the actual turbine output m dot h1 minus h3. Recall, m dot h1 is the energy carried by the flow into the turbine, and m dot h3 is the energy that is leaving the turbine in an actual turbine. And so that becomes m dot cp t1 minus t3 for the PG model. Again, from handout J you can figure that out. It's written in the under the PG model, these formulas. Substituting 5 kg, let's take a value of cp to be this 873 and 493, and the answer turns out to be 233 kilowatt. As a matter of fact, I just checked these numbers and it is indeed 1906 kilowatt. So now that we have the actual power and the ideal power, the thermal efficiency we can easily obtain. The turbine efficiency, or the isentropic efficiency, is obtained as turbine efficiency w dot turbine. Now, which one goes on top, the actual or the ideal? Obviously, the ideal power is much higher than the actual power, and that's how the isentropic efficiency is defined. So we divide the two numbers. One is 1906 and the other is 2521. And that's approximately equal to 0.75 or 75%.